welcome to the lecture 4. This is basically the continuation of the lecture 3, where we started to discuss about the chemical structure or basically the to understand the microstructure of the polyethylene and polypropylene, where we started to discuss in the last class the tacticity, that the microstructure associated with polypropylene or the similar type of polymers, and we saw that if you start from a let us say like a prochiral molecules like this one, okay, that is the propene. Okay, you know that all of you know these molecules, okay, the acetophenone. So, this is also a prochiral molecules. So, this is the sp2 center, okay, and if it is, if we can make the sp3 centers by putting another substituents on this one, then it will be like that. Okay. So, this is my CH2, okay, and this is my hydrogen, this is my methyl, and let us say this is my X and this is H and this is H. So, now you will see that this is sp3. So, now you have the different 4 groups are there. So, it will become the stereocenter. So, this kind of prochiral molecules will give chiral by putting another substituent. So, similar thing happens if you see carefully, that if it is this is your propylene molecules, and if you do the polymerizations, okay, and you end up with this situation where your, so here it is methyl, here it is here another hydrogen, and here the chain with different carbon, here also chain of different carbon. So, this kind of polymers, this is the polypropylene, okay. Here you will see the stereo regularity issues. Okay. Now, depending on the orientation of the metal orientation of the methyl group, okay, you will get different kind of stereo regularity that we discussed in the last class. And the interesting point is that we in the last class we discussed the we can get the isotactic, we can get the syndiotactic, and we can get the atactic, and this one is the crystalline, and this one is the amorphous. Okay. And that is why you will see that this atactic polypropylene is quite, if you heat it, it becomes soft, quite soft in nature, and these are relatively harder. So, you will see that depending on the microstructure, you can get the different properties, and then you can basically do your applications according to the properties. Now, we will try to understand about more about the microstructure and how to detect the microstructure, the tacticity by routine spectroscopic methods. One way is the proton NMR. So, in the last class we discussed how you can assign by simply the chemical shift of the CH2 protons in the repeating units of the polypropylene. Okay. And we explained that why the chemical shift is different for the isotactic or syndiotactic scenario. So, we will discuss in more depth today. So, let us again. So, this is my propylene, and I am doing the polymerization, and I am getting this polypropylene polymer. Okay. So, let us the 3 scenario. will get, oh sorry, okay, please try to understand, okay, and please also do practice yourself. Now, here this is so this is my R, 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 and this is R, S, R, S. Okay. Now, another scenario. Okay. Like that. So, this is my R, R, S, R, like that. Okay. Now, if you consider the this CH2, okay. So, here we have assigned R is on the basis of the stereocenter. Now, consider this CH2. So, this one will be M, this one will be M, this one will be M, like that. So, this one now will be, okay, this stereocenter is based on the RS descriptor, and this CH2 is the small r, racemic. This R means racemic. So, this is R, this is R, this is R, okay. And here according to this convention, that CH2, so this will be M, this will be R, and this will be R. Is it clear? So, this is basically if you see like that. So, this by H, and if methyl group, let us say the above, and this one so this is, let us say this one, and methyl is below H, and this is my H. Okay. Now, you will see that this in this case methyl and methyl group is above the plane. So, this is same configuration. So, R, and this is R, and this is S. Okay. And this is the meso. Why? Because if you imagine a plane crossing this CH2, so you will see that here, so like this plane, so you will see methyl is above, H is the below. So, you will get the meso, and like this one the scenario is different. Okay. So, that is why this is R, small r, racemic, and this is M. So, for simplicity, we generally do, we follow the easier convention. So, we just, instead of writing on to show the stereo center, we just write is a linear form like that one. So, if it is like this one, so like this like that, and for this one this like this one, sorry, like that, and this one we write like this way, this way, this way, this way. Okay. So, this is the simple convention we follow to represent the tacticity in the polymer backbone. So, if methyl group is oriented above the plane, we just put the line this is your main chain of the PP, okay, and we just put this methyl group is a upward, and if it is the below, then we put is the downwards like that. Now, so we put it like this and we write like M in the middle, M like that, and here same way. So, here we will put the R, same way what we put, we will put M, we will put R, we will put R. So, this is the convention we follow, okay, for representing the tacticity in the polymer backbone. Okay. So, let us discuss in more depth, because this concept will be used, will be very useful when we will do the mechanism study and to understand the mechanism by a particular polymerization protocol, and here we will discuss in more depth the polymerization by the Metallocene based catalyst, because that is one of the biggest or you can say the biggest beauty of the Metallocene catalyst, that how we can get the stereoregularity of the polymers if we use a prochiral monomers, which are not possible if we do the other conventional polymerization like radical polymerization like that. So, that is why it is very important to understand the tacticity, otherwise we cannot detect by the routine spectroscopic methods, and we cannot understand that what kind of polymer it is. So, let us take very small fragment of the propylene. Okay. Let us say just like two repeating units. So, just a 2 repeating units. So, one is the methyl groups are on the same orientation. Okay. So, this is called the dyad. Okay. So, this is and another one I am taking like this and this one. Okay. So, this is called a dyad, okay, tacticity. Okay. I am just taking only the 2 repeating units of the polymer of the polypropylene backbone, okay, to understand the tacticity. Okay. Now, so this is then if we represent like a line. So, this is meso. So, this is in the middle, it is CH2. So, this is called the mesodiad. This is called the mesodiad. Okay. And this is then the opposite one. So, these 2 methyl groups are in the opposite direction, opposite orientation. So, if this one, then it is a if we represent by line. So, it would be like this one, and this is this CH2 is represented as R, and this we call the racemic dyad. Okay. So, this is isotactic fragmentation of a isotactic PP. Okay. And this is a fragmentation of a syndiotactic PP. Okay. Now, you will see, now if I go to the dyad to triad tacticity. Now, what will be scenario? Let us try yourself. Okay, you can try yourself. So, what will be the difference? Okay, then you add one more unit. So, here put the methyl, then the methyl, another possibility, Okay. So, here like that, alternate orientation, and another one, okay, like that. Okay. Now, can you label the tacticity as I did for the diode? You can try yourself. So, let us do it. So, first thing you represent as a line. So, here, 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 okay, like that. So, here like that, and here, here, here is like that. Okay. So, you can put it as a M. So, this is R, this is R, and this is M, this is R. Okay. Easy. Okay. So, here you will see that M. Okay. So, this is isotactic, triad. Okay. This is R. So, this is basically syndotactic, and what is this? Obviously, this is atactic. Okay. This is M R. Okay. Now, go to the, so this we did with a very small fragment to understand. Now, in the polymer it will be quite big. Okay. So, now let us do in a, to understand in a bigger chain. Okay. To just to understand, let us take a like a 8, 9 or 10. Let us take 8. Okay. So, what will be the scenario? We will just draw it. Okay. Just draw it with 8 diodes. So, we know the diode, we know the diode, we know the triad. How does it happen? Now, let us try with 8 repeating units. How does it happen? So, what will be the scenario? So, let us make the first the main skeletal chain represent as a line, and we put like let us take 9 repeating units. Okay. So, 1, 2, 3, 4. Okay. And let us take this one. Okay. 1, 2, 3, 4. Okay. Now, label it. Label it as a small m and small m and small r convention. So, this will be your m, stop here, this is r, this is r, this is again m, this is again m, this is again m. Okay. So, this is the scenario. Why we are trying to understand? Because when we will discuss in later part that how we can control the stereoregularity by following the two mechanism. One is the catalyst site mechanism, and one is the chain end control mechanism. Okay. So, in one case you will see that the catalyst is chiral and it will induce the stereocenter because the catalyst is a chiral, and one case chain end control, the catalyst is not chiral, catalyst is achiral, but you are getting the stereocenter. This is very funny. Okay. So, in one, if your catalyst is chiral, then obviously, okay, you will get the chiral center. Okay, for this we will discuss this one. This is very interesting. So, but if your catalyst is not chiral, then what we will get? If it is not chiral, in many cases, if it is not if catalyst is not chiral, then also you can induce the asymmetric synthesis. In organic chemistry, you have heard the asymmetric synthesis and how it is possible. We will discuss in the next classes or so. Okay. So, in our polymerization by Metallocene chiral or achiral catalyst, you have to have a good concept of this tacticity, because by this way only you can study or you can conclude that in which mechanism this catalyst, this polymerization is happening, whether it is a catalytic site control or whether it is a chain end control. Okay. Fine. So, here you will see that now I am asking two questions. Okay. You have to do now itself, okay, on the class, that how many diodes. The question is that you find out the diodes and triads and label it. How many, first how many diodes, and then you label how many what label according to the small m small r configuration convention, and how many triads and label it as a MR convention. Okay. Let us try. Okay. Let us do it. So, first what you have to do, we have actually done the main part, we have done it. Now, you will see this is if first you see the diode. So, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, 8 diodes. Okay. Is it clear? So, I am getting the 8 diodes. So, diodes is number of total number of diodes is 8. Now, can I tell that how many triads from here? Okay. Let us do it. So, this is how many? This is 1. Okay. This is 1. This is 1. Now, this is 1. Now, this is 1. Okay. So, like that you will have a triads total how many? 7, like that. So, 8 diodes and triads. Now, you find out what type of diodes. So, here you will see that this diode M. Okay. So, M, I am first trying diodes. So, how many mm? 1, 2, 3, 3, 1, 2, 3, 3. Okay. So, 1, 2, 3, 1, 2, 3. So, here total 6 M diodes. Okay. Sorry, here I have to, I should not write the double M, it will be single M, because it is a diode. Okay. Now, total now 6 assigned as a M, and this left over is the R. So, R is 2. So, total is 8, clear. So, out of 8 diodes I have the 6 M and 2 4. Now, let us say triads. Okay. So, you will see one triad is M. So, here you will see M, then M, then M R, then R R, R M, M M, M M like that. So, if you calculate the triads, how many you are getting? So, let us see. Okay. So, you are getting the, let us first MM, okay, this MM. So, 1 mm, this is 1, this is 2, okay, and here this is 1, this is 2. So, total I am getting the mm, I am getting the 4. Okay. Now, you are getting RR, how many? RR, this one and this one. Okay. So, RR I am getting only 1, that is triad, only 1. Now, how many MR? Okay. How many MR? Where MR I am getting? Here you will see MR and MR. Okay. So, again 2. So, total 7. Okay. So, here you will see that in this case for diode, if you see the ratio for diodes, M by R ratio is how much? Is it? This is the M and this is the 6 by 2. Okay. 6 by 2. Okay. And in this is the M by R, and we also represent in like this way. So, like M, how much the mm? Okay. I am getting the ratio with respect to the total number of diodes. The M I am getting 6 by 8 and R I am getting 2 by 8. Similarly, I am getting like in a first bracket, that is the convention. So, 4 by 7, R I am getting 1 by 7 and M R I am getting is 2 by 7, like that. Okay. So, as I told, why we are studying? Because I already discussed that the chemical shift of these protons, these 2 protons, okay, will be different if it is isotactic moiety or whether it is a syntactic moiety. Okay. For isotactic moiety, as I already discussed, that you will get here different chemical shift, but in this case, okay, you will get a same chemical shift, because you will see this will, as in the last class I have discussed, that if you have like this and this, you will have this hydrogen is a below, this is methyl, this is a below, okay, and here this hydrogen, this is the above and this is the above. So, this one will experience different chemical shift, we will experience the same chemical shift in proton NMR spectroscopy for the racemic diode, that is the syntactic fragment. So, with by calculating the number of by carefully checking the chemical shift of these 2 hydrogen protons and then relating with the diodes and triads, you can calculate or you can determine the microstructure of the polypropylene or related polymers, okay, by proton NMR spectra. As I told, obviously, you have to use 400, 500 or 600 megahertz high resolution NMR to get the knowledge or the information about the tacticity. Okay. So, this is as I told that this is very interesting and you have to understand the logic behind the determining the tacticity of the polymers. Obviously, as I told that you can also get the knowledge whether it is a syntactic or isotactic or atactic by other physical properties, as example for the stiffness, the crystalline nature of the polymer, but this the spectroscopic method, the proton NMR and also C13 definitely, okay, as I am discussing proton NMR because this is more easy to record, easily available. So, combination of the proton and obviously combination of C13, you will have we will have a good knowledge about the tacticity of the polymers. Okay, fine. So, now we know that what is the basic convention to represent the tacticity of the polymers where the stereoregularity exists in the polymer backbone. So, similar, if you understand here that in the polypropylene this was the methyl, okay, and in the polyvinyl this is the chloride in place of vinyl. So, obviously, okay, the similar kind of stereochemistry is also may also be observed in polyvinyl chloride. Why we are discussing PVC? Because you know that if you see look around your classroom, you will see that many cases in this room you will get the PVC material, the tiles, okay, the pipes, okay, all are made of the PVC. It is a very popular polymers. Okay. So, I am not discussing in depth about the application and others, I am more discussing about the chemistry of the polyvinyl chloride. Okay. So, as I told that these also exist because you see that very similar to the propylene, polypropylene. If you understand the polypropylene then you will understand the PVC. So, same concept. Here. So, here also same concept. So, you just put chloride here in just a chloride here. Okay. So, this is basically a fragment of the PVC polymer. So, here you will see same way you can do. So, this is isotactic, this is syntactic, and obviously this is the atactic. So, in the PVC also the stereoregularity is possible in PVC polymers, because here we are using again the prochiral monomers. So, this is your monomers, okay. So, this is also prochiral. Okay. So, I think now we have a good knowledge about the microstructure, what is the origin of the microstructure in the polymers. So, not only the microstructure, you will see that different type of regioisomers are also possible, and that is also govern the polymeric the properties. As example, if you see the polybutene, this is also another polymer heavily used polymer in the category of polyethylene, polyolefin, sorry. So, here also you see that purposely we use is a mixture of the butene. Okay. Here I have shown only with one butene, that is the alpha olefin. Okay. That is we use the alpha olefin. So, this is the polymerase like that, and you will get the polybutene. Okay. But if there is a mixture of the butene, because you would show that you know that 3 kind of butene are possible, okay, depending upon the position of the double bond. So, this is one. Okay. So, sorry. This is one, that is a 2 butene, and another one is the oh, sorry, I am okay. So, here you will see this is the 1 butene, this is the 2 butene, okay, and this is the isobutylene. So, all are basically butene, and obviously depending on the monomer, the polymeric structure will be different. Like this one is from the alpha butene, that is a 1 butene. So, depending on the ratio of the different monomers, you can also tune the physical properties. Okay. The applications I have listed. Okay. The applications are quite huge. I am not discussing the application. I am just trying to emphasize the chemical structure of the polymers, the common polyolefin polymers we use in daily life. Okay. So, another one is a very famous polymers and very interesting. You can say the polyisobutene is naturally occurring polymers. Okay. You know all the Robert Press, we can get the polyisobutene from there, and also we can synthesize the polyisobutene very easily by radical or anionic polymerations. So, here also you see that very interesting, here 2 kinds of olefinic bonds are there in the isoprene. Okay. So, here you will see that here. Okay. So, here is one double bond, here is double bond. So, polymerization may occur here or here or here. Okay. So, depending on, and also it can undergo the isomerization. So, depending on that one, you can get a mixture of the polyisoprene, all are polyisoprene, but if you see very carefully, the chemical structure will be different. Okay. And all are possibilities are there depending on the polymerization protocol. Okay. And also definitely the stability of the olefinic bond. So, here you will see this is cis 1,4. Okay. This is cis 1,4 because here you will see this is the cis, this is the trans 1,4. So, here you will see this is the trans, this is the cis. Okay. This is 3,4 addition. Okay. So, here you will see this, if I 1, 2, 3, 4. So, this is you will see that 1, 2, 3, 4 okay, from here. So, if I start from here 1, 2, 1, 2, 3, 4, here also that is why it is called 3, 4 addition. This is the 3, 4, 3, 4. Okay. So, 1, 2, 3, 4. Okay. So, this is the 1, 2 addition, that means this one. Okay. So, the polymerization is through 1, 2 addition. Okay. So, this through this one. So, this is 1, 2 addition, and this is 3, 4 addition, that is the this way, this is 1, 2 this way. So, you will see that depending on the polymerization protocol, this statistical distribution will be different, and the polymerization properties, the polymer properties also will vary to some extent depending on the ratio. And you know, this polymer was very famous from quite earlier days, because this is heavily used in the tire industry, particularly when the Charles Goodyear discovered the vulcanization of the rubber using sulfurate, and basically he took the advantage of this extra olefinic bond and did the change the physical properties of the polymer to make the more stiff in nature, because you know that this the polyisoprene is rubbery, it is quite soft. Okay, the Tg is temperature is quite low. So, from here it is very clear that depending on the polymeric chemical structure, the properties of the polymers are highly varied. So, you will see that the properties of polymers okay. Here specifically I restricted on polyolefin type of polymers are governed by chemical structure. These chemical structures may be two types, one is the regioisomeric and one is the stereoregularity. So, we discussed the regioisomers, we discussed the stereoisomers or stereoregularity, and we discussed the tacticity, that is basically coming from the stereoregularity or stereoisomers of the polymers, where the monomer is the prochiral in nature, and we try to understand the microstructure present or possible in the polyolefin type of polymers. So, why it is important? Because these are important, because if you target for applications, you have to know about the properties of the polymers, and you have to know that how to engineer the polymer backbone. So, with this knowledge, in the next class we will try to understand the polymerization protocol, because as I told that the polymeric, the chemical structure you can control by the polymerization protocol by using the same monomer. So, that is very important to understand the different available polymerization protocols, and then the common polymerization protocols, and then we will go into our main content of the of this course, that is the organometallic catalysts are used for making the polyolefin in industry. Okay, that is the Metallocene and the Graph type of catalysts. Okay. So, thank you very much, and we will see in the next class.